Have you ever looked at a pile of wood chips and seen jet fuel? Or maybe electricity for your home? It sounds kind of like magic, but it's pure science. Today, we're diving deep into something called thermochemical conversion, which is really just a fancy way of saying we're turning plants into power using some serious heat. Let's get right into it. So let's start with a simple pile of biomass. It could be wood chips, corn stalks, pretty much any plant matter. But here's the big question. How can that one single pile become three totally different things? We're talking about direct heat, a liquid fuel that could run an engine, and even solid charcoal that can improve our soil. That's the puzzle we're going to solve today.
And here's our roadmap for how we'll do it. First, we'll get a handle on what thermochemical conversion actually is. Then, we'll look at the three main ways to do it: combustion, gasification, and pyrolysis. And finally, we'll figure out how you decide which process is the right one for the job.
Okay, first things first. Let's lock in our key term. What in the world is thermochemical conversion?
You can think of it like a toolkit, and the main tool is heat. And we are talking about some serious heat. Anything from a relatively mild 200 degrees Celsius all the way up to a blistering 1200 degrees. This heat isn't just burning things, it's acting more like a chemical scalpel. It slices apart the bonds inside the plant matter and lets us rearrange the atoms into something new and really useful, like a gas, a liquid, or a solid energy source.
So how do we control what we end up with? Well, it really all comes down to three main levers. First, temperature. Just how hot are we going to run this thing? Second, the oxidizing agent. This one is critical. How much oxygen are we going to let into the party? And third, time. How long do we let the process cook? By tweaking these three variables, engineers can steer the chemistry to get exactly the product they're looking for. Let's see how that works in our first process.
All right, our first option is the one we're all familiar with: combustion. You can kind of think of this as the brute force approach. It's direct, it's powerful, and hey, we've been using it for thousands of years.
At its core, combustion is really simple. It's just rapid, complete oxidation. You take your biomass, you give it way more oxygen than it technically needs, and poof, it releases all of its stored chemical energy in one big burst of heat. It's the most direct way to get the energy out, kind of like cashing your entire energy paycheck all at once. Now, on an industrial scale, this is way more than just a bonfire. Stoker boilers are the workhorses, feeding fuel onto a moving grate. A more advanced option is a fluidized bed combustor, which actually burns the biomass in a hot, churning bed of sand. It's cleaner and more efficient. And, one of the fastest ways to use biomass for energy is co-firing, where you just mix it in with coal at power plants that already exist.
But, and this is a big but, here's the catch. When you use that raw heat to boil water, to spin a turbine, to make electricity, you run into a wall. It's the fundamental limit of the steam cycle itself. And the result? A typical biomass power plant only manages to turn about 20 to 35% of the fuel's energy into actual electricity. So yeah, it's direct, but a whole lot of energy gets lost along the way.
Okay, so let's move on to our next option, which is, well, it's a lot more elegant. If combustion is brute force, then gasification is the alchemist's choice. This is all about transformation, not just raw energy release.
Now, the absolute key to gasification is this. We're not trying to burn the biomass. We're trying to turn it into a super useful combustible gas called syngas. And the trick is to react the biomass with a very controlled, limited amount of oxygen. We're deliberately starving the reaction of air. By doing that, we force the chemistry to go down a completely different road. And this syngas is incredibly versatile. It's not just fuel. It's like a chemical Lego set for building everything from hydrogen to synthetic liquid fuels.
Let's take a little trip inside a gasifier. The biomass goes on a journey through 4 different zones. First, it gets dried out. Then it hits the pyrolysis zone, where it breaks down into gases and a solid called char. Next, in the super hot oxidation zone, a little bit of that char actually burns to provide all the heat the process needs. And finally, in the reduction zone, the hot gases react with the leftover char to create the valuable stuff, our syngas.
And what's so cool about this is the beautiful balance inside the reactor. You've got some reactions, like the ones on the left, that release heat. That heat then powers the reactions on the right, which actually need heat to turn things like CO2 into valuable fuel gases like carbon monoxide. It's like a self-sustaining chemical factory where one set of reactions is constantly fueling the other.
Okay, that brings us to our third and most versatile option: pyrolysis. If gasification is the alchemist, then pyrolysis is the ultimate transformer. It can do some amazing things.
So here's the big difference.
Pyrolysis is what happens when you heat biomass up, but in the complete and total absence of any oxidizing agent. No oxygen. None. Zero. So instead of burning or gasifying, the heat just cracks the biomass apart into its basic components, which we can then capture as a liquid, a solid, and a gas. And this is where that time lever we talked about becomes so important. If you pyrolyze slowly at lower temperatures over a long time, you get the most solid product, biochar. This stuff is amazing for soil health and for locking up carbon. But if you do it incredibly fast, we're talking heating the biomass to 500 degrees in less than 2 seconds, you totally change the outcome and maximize the liquid product, bio-oil. And that's huge because this bio-crude can, with a little upgrading, be dropped right into our existing oil refinery system.
So, if you follow that slow path, you can see the results right here. Cooking the biomass low and slow gives us a huge chunk of solid biochar, almost 40% of the total output. This is exactly what you want if your main goal is to store carbon or make great soil.
But now, watch what happens when we switch to fast pyrolysis. The output completely flips on its head. All of a sudden, we're not making char anymore, we're running a liquid fuel factory. We get a massive 70% of the product as bio-oil. It's the exact same starting material, just a radically different recipe. Okay, so we have 3 really powerful options on the table. How on earth does an engineer decide which one to use? Let's put this last piece of the puzzle into place. It really comes down to a series of engineering trade-offs. You see, if your biomass is wet, like fresh-cut wood, combustion is probably your best bet since it can handle the moisture. If you need a flexible chemical building block, you're going to want the syngas from gasification. And if you're after liquid fuel or that solid carbon, pyrolysis is your answer. Each path has its own needs, its own products, and its own challenges to solve.
Ultimately, it just boils down to this. There is no single best process. There just isn't. The right choice depends completely on what you're starting with, what you're trying to make, how big your facility needs to be, and of course, whether the numbers add up.
And that leaves us with a really fascinating final thought. We have the technology right now to turn plants into direct power, into advanced fuels, or even into a tool for pulling carbon out of the atmosphere and putting it back in the ground. The science is there. The question isn't if we can do it anymore. The real question is a strategic one. Which of these powerful paths are we going to choose to build a more sustainable future? Thanks for watching.